especially Lucas, for the kind invitation. So today I'm going to talk about non-equilibrium thermodynamics and many-body dynamics in open quantum system. So this is the outline of my talk. Actually, this talk consists of two topics. First, I will talk about continuously monitored many-body dynamics, so how many-body dynamics behave under observation, by focusing on quantum statistics, criticality, full counting dynamics, and also I'm going to talk about how summarization proceeds along single quantum trajectory, not an ensemble level, but single quantum trajectory. And on the second topic, let me introduce a recently performed test on information thermodynamics using a superconducting qubit. So the first topic is continuously monitored many-body dynamics. The main player of this work is Yuto Ashida in collaboration with Shunsuke Furukawa. So this work was motivated by the development of quantum gas microscope, which enables observation of many-body wave function at a single site resolution. So here, this is a snapshot of a many-body wave function, and each bright spots show single atoms. So, but at such high resolution, of course, the Heisenberg's uncertainty relation must be considered. So if the position is so accurately measured, back action on momentum will be huge. Then we may expect that higher the resolution, the greater the back action will be. Well, conventionally, we consider statistical mechanics because we give up individual information of atomic motion. So we only consider the collective motion. Now, technology enables us to locate individual atomic motion. Then the question is this. So how are the many-body dynamics and the quantum phase transitions altered by the measurement of back action? So the frontiers of quantum gas microscope requires the generalization of quantum statistical mechanics that incorporates not just the effects of collective motion, but also the effects of measurement back action. So I think this is one frontier of statistical mechanics, which I'm going to talk about. So the model we consider is continuously monitored. We continuously monitor atoms on an optical lattice. And here, on atomic gas, we shine off-resonant laser, and this light is scattered through optical lens and detected on a screen, usually CCD camera. Then the measurement operator is given by this. Here, the gamma denotes the strength of interaction, and F is a point spread function which shows how an atom at this site propagates through this detection areas. So this is specified once optics is specified. And N sub M is the atom number operator at site M. The dynamics of atoms under continuous monitoring is governed by three terms. One is a unitary evolution. Okay, this is just the usual Schrödinger equation. In the following discussion, we consider H is a Bose-Hubbard Hamiltonian. Then there are two events. One event is a photon is detected somewhere here. The other is photon is not detected at some instant of time. In both cases, the state evolution is non-unitary because we continuously monitor information from the systems. So when in the absence of photo detection, the state evolution is given by this, which is non-unitary, which reflects the fact that no photon is detected. And the second process is when a photon is detected, then there is a quantum jump. The state changes this manner, where M is a measurement operator. Okay. So this is a stochastic evolution of the wave function, many-body wave function. Okay. So we take the continuous measurement limit by assuming the frequent and weak measurement limits. by frequent, I mean that measurement rate, gamma, is much larger than the hopping rate of atoms. Okay. And by weak, I mean that spatial resolution of the detection is much, much larger than the lattice constant. So if we sharply measure the atomic systems, the atomic system will be destroyed instantly. This is something we don't want. So we very vaguely observe the atomic systems so that continuous measurement is possible. One might wonder that if the resolution is so bad, then can we resolve the individual atoms? The answer is yes. If we observe the systems for quite a long time. So this is one example. So initial distribution is broadly distributed. But if we keep measurement for quite a long time, the wave function collapses to 2 points. In this case, we know that at the end of the day, there are two atoms at this location and this location. Okay. But the point is statistics. So even if the resolution is bad, if you keep watching, then the statistical accuracy goes up. Okay, so now let us first consider the case of distinguishable particles. So the distinguishable particles are distributed on optical lattice, and we measure. The continuous measurement theory of distinguishable particles can be simply a generalization of single particle model due to DOC. So DOC some 30 years ago considered the case, what happens if we keep observing a single atoms in free space? Okay. Single atoms, without measurement, the wave function spreads in time due to Heisenberg's uncertainty relation. DOC identified that if you make the observation, then there's a wave function collapse. Okay. If the strength of measurement is relatively weak, then wave function collapse is not complete. So then he found that there is a compromise between wave function expansion due to Heisenberg's uncertainty relation and wave function collapse due to measurement back action. And eventually he found that there is some solitonic wave, stable wave, will be formed under the action of continuous measurement. Okay. Now, the many particle extension is rather straightforward. So we, as before, we have a unitary evolution. This describes the spread of wave function. And since the particles are distinguishable, so both center of mass, so this is the center of mass position operator of an atomic system, and the relative positions between two different particles, both decoheres, according to this master equation. Physically, this is rather straightforward because all degrees of freedom can be distinguished in this case, therefore susceptible to measurement back action. Then what happens if two particles are indistinguishable, like the case when two particles are both rubidium atoms? Okay. In this case, there is one important distinction. So dislocation and dislocation cannot be distinguished. So in both cases, center of mass is here, but relative positions changes sign. In quantum mechanics, we know that when two events are indistinguishable, then probability amplitude must sum up. As a consequence, the relative positional term disappears due to destructive interference of multi-particle probability amplitude. And only center of mass decoheres. So there is a big difference between distinguishable and indistinguishable particles. So multi-particle quantum interference suppresses relative positional decoherence, and only center of mass coordinates decoheres. Okay. To perform numerical simulation of quantum walks, so we consider two atoms in optical lattice. Initially, they locate at adjacent lattice sides. And then we let the system evolve freely, subject to continuous monitoring, and see what happens. We examine 3 cases: distinguishable particles, fermions, and bosons. First, without measurement, then this panel shows the results of numerical simulation. Okay, so this shows that this time location. So 2 atoms just propagates away. And this behavior is almost similar regardless of the statistics and the distinguishability. In all cases, they just 2 particles move away in opposite directions. Simple. But under continuous measurement, for distinguishable particles, they behave very differently, because every time a position is identified, there is a measurement back action. And the measurement back action is random because this is a quantum. So they behave very random walk, something like this. Okay. For fermions, it looks like this. Okay, very regular. Center of mass is preserved, and they move in opposite manner because of Pauli exclusion principle. And for bosons, they move away in the same direction because of bosonic stimulation. One photon is detected, another photon is likely to be detected in the same mode. This is a boson. This is how lasers occurs. Okay. So we know that behaviors are very different in those 3 cases. And even for 2 particles, behaviors are so different under continuous measurement. So we would naturally expect that in many body cases, we would have a very different, qualitatively different behaviors because of this measurement back action. So let me now discuss this problem. The first is a quantum critical phenomena under continuous observation. So the model we consider is a continuously monitored quantum many-body system. So this is very schematic. So a single quantum trajectory undergoes continuously, and sometimes there's a quantum jump, and then some continuous non-unitary behavior, and then there is another quantum jump, and et cetera, et cetera. So let me first discuss the case of continuous time evolution between 2 quantum jumps, because quantum jumps introduce some extra consideration. And then the evolution between quantum jump is described by this non-Hermitian Hamiltonians. So this is the usual Hermitian Hamiltonian, but because of the measurement back action, even if no quantum jump occurs, the state evolution becomes non-unitary. So the M is the measurement operator. Okay. So the analysis of quantum critical phenomena is usually to analyze this. But now we need to analyze non-Hermitian Hamiltonian. So this is the task we have. So because the Hamiltonian is non-Hermitian, energy spectrum becomes complex. The real part we interpret to be an effective energy of the system. The imaginary part is a decay rate. Actually, this is not so unfamiliar. This is very familiar in, for example, nuclear physics. In the nuclear physics, if we look at some particle, but it's strongly interacting with other particles. So it's like observation of a single particle by other particles. As a result, the energy levels of the nuclear system is broadly distributed, and the center of mass, the real part, we interpret as an effective energy of that particle, and width determined by this gamma, we interpret as a decay rate of that metastable state. Okay. And the ground state we identify as a state having the lowest energy. And in our model, this ground state turned out to have a minimal gamma, hence the longest lifetime. So if you keep watching, the state decays, but the longest lived state is a ground state. Okay. And we consider the situation in which the Hermitian part of the Hamiltonian exhibit quantum criticality, which we are interested in from a statistical mechanical point of view. Okay. So first example is a superfluid Mott insulator transition in the Bose-Hubbard model. So this is a Bose-Hubbard Hamiltonian. And in this case, two-body loss due to inelastic collisions is a major dissipative process experimentally. So this is a non-Hermitian Hamiltonian. And the superfluid Mott insulator transition point is identified with the point at which energy gap closes. So this is also in line with conventional definition. Okay, so this is the results of our numerical simulation. So the horizontal line shows the measurement strength, and the vertical axis shows us how much the critical point shifts as a function of measurement strength. So this result shows that this is the Mott insulator regime, and this is the superfluid regimes. The Mott insulator regimes expand as the measurement strength increases. And this expansion of Mott lobe may be interpreted as being caused by the suppression of hopping due to continuous quantum Zeno effect. So we know that if we measure the positions, the particles cannot move so quickly. So this is the quantum Zeno effect. If you keep watching, the hopping rate will be suppressed, more suppressed compared with the on-site repulsion. So this is why the Mott lobe expands. Okay, so quite natural. And actually, this has been recently being observed by the Kyoto group. The next example is a quantum critical phenomena of a 1D Bose gas. And in this case, the process is again the two-body loss. In one case, the Hamiltonian is given by this Lieb-Liniger model. And because the loss is also the same, so we can simply introduce the effect of loss by introducing this imaginary part. The nice thing of this 1D system is that we can analytically analyze the system using this low energy effective model, which is a Tomonaga-Latinger model. The only modification is that because this is complex, so there is a complex phase which is introduced because of this measurement process. So then we can only analyze this. Okay. So we examine the behavior of two critical phenomena against the measurement strength. So one is a one particle correlation. So this is which measures the long range order. And this long range order decays algebraically in 1D systems with some critical exponent given by K phi. Another measured quantity is a density-density correlator, which again decays exponentially with some critical exponent, K theta. In the Tomonaga-Latinger case, those two critical exponents are equal. So this defines the Tomonaga-Latinger universality class. So this panel shows how those critical exponents, K theta and K phi, behave as a function of measurement strength for weak and strongly interacting case. When the measurement strength is 0, then the two critical exponents are the same. But with measurement strength increases, then the two critical exponents bifurcate and take on different values. Now we have two critical exponents, which indicates the emergence of a unique 1D quantum critical phenomena class, universality class, which is different from the Tomonaga-Latinger universality class. And this new universality class emerges because of the effects of measurement back action. So now we know that measurement back action is not just disturb the system, but to create a new universality class in statistical mechanics. So let us now discuss the full counting many-body dynamics towards establishing a statistical mechanics under continuous observation. So now we take into account quantum jumps as well. Then the full quantum dynamics is something like this. So we are interested in the probability distribution P sub n of t, which gives the probability of observing n quantum jumps during a given time interval t. So to address this question, we initially prepare n atoms, say in optical lattice. Then we let the system evolve subject to measurement back action. Then some atoms will be lost. In our case, we assume just one body loss. So some atoms are lost. Once quantum jumps occurs, then this atom heats up and go out of the trap. And at the end of the day, we measure the remaining number of atoms by means of quantum gas microscope. If n minus n atoms remain in the trap, then we find that small n atoms undergo quantum jumps and goes out of the trap. By repeating this process, we can measure, we can determine the full quantum dynamics, which describes the ensemble of quantum trajectories for the varying number of quantum jumps. So this can in principle be determined by performing such measurements. So to be specific, we solve the Lindblad-Master equation. Here, H effective describes the Hermitian part of the Hamiltonian and non-Hermitian term due to quantum jumps described by L. And the second term describes the quantum jump event. So we now take into account this quantum jump process. This master equation can formally be solved something like this. Okay, so this is a very formal quantum trajectory formalism. Okay. And this solution describes an ensemble of all possible trajectories of n quantum jumps. In principle, yes. But in general, it's hard to analyze this because of this practically calculating this quantity. So to identify the phenomena unique to full quantum dynamics, we consider a solvable model, which is free fermions under periodic dissipation. Okay. So this can be solved analytically. So we consider half-filled fermions initially in the superlattice, and on top of that, we introduce some dissipative potential, which models one-body loss. Then we perform side resolve detection using quantum gas microscope. So in this model, the Hamiltonian, effective Hamiltonian, actually involves the PT symmetric Hamiltonian described by this, and the jump term described by this. And for this case, full quantum, exact solution of full quantum dynamics is available. So we can analyze this. So we use this solution to study how correlation propagates after the quench. So we first consider the equal time correlation at site L and at site 0. Then at the ensemble level, so we initially consider the ensemble averaged quantity, and this is how the state propagates in time. This is time, and this is the lattice site. Then there are many propagations on the ensemble level, but all the data falls within this Lieb-Robinson bound. So we know that at the ensemble level, the propagation of correlation is indeed limited by the Lieb-Robinson bound. So it's consistent with conventional wisdom. And this panel shows the same quantity, but subject to individual jump process. So when there is no quantum jump, then the distribution something like this, 10, 20, 30, and 40 quantum jumps. The behavior is something like this. So we find that here, not just the Lieb-Robinson bound, but at integer multiple of Lieb-Robinson bounds, there are data. So in the presence of measurement, the particles propagate beyond the Robinson bound. So what is the physics? So physical origin of such supersonic propagation is a PT symmetric non-Hermitian dynamics. So PT symmetric Hamiltonian is non-Hermitian, but nice thing of this PT symmetric Hamiltonian is that eigenstate can be real for some parameter regimes. Okay. But there is a compromise. So although the back action, eigenvalues can be real, eigenstates must be non-orthogonal, because otherwise the Hamiltonian becomes Hermitian. The nice properties of Hermitian Hamiltonian, we think Hermitian Hamiltonian because of two properties. One is the eigenvalues are real, and the eigenstates belonging to different eigenvalues are orthogonal. In the PT symmetric case, Hamiltonian is non-Hermitian, and the eigenvalues can be real, but eigenstates must be non-orthogonal. Then this is a typical dispersion relation, and for a given wave number, then there are 2 points having the same wave number but having different eigenvalues. In the Hermitian case, they are orthogonal, so independent of each other. But in the PT symmetric case, they are non-orthogonal. So there are oscillation between those two cases. So there are norm oscillation at frequency twice the energy of this state. Now, the velocity, group velocity is given by the derivative of energy with respect to momentum. So if the energy now has norm oscillation involves higher order harmonic of 2 times epsilon, then the corresponding velocity also have higher harmonics of 3, 5, and 7, something like that. So this is the physics. So non-orthogonality of the Hamiltonian caused by measurement back action produces such high frequency and beyond Lee Robinson propagation. Okay, so this is a conference of thermalization, thermodynamics. So one might be interested in how do thermalization and heating proceed at a single trajectory level. There are 3 distinct types of thermalization in physics. Conventionally, we assume that systems are in contact with thermal reservoirs. So this is a conventional setting. More recently, we are interested in thermalization in isolated quantum systems. Okay. The typicality argument, many other interesting ideas emerge in this field. But there are third types which I'm going to talk about, is systems under control and measurement. So we want to control quantum systems, then we have to perform measurement. Then there is a measurement back action, and how the system evolve under such situations. Experimenters know this for quite a long time because they perform measurement, and they worry about heating due to the measurement process. But how to quantitatively describe this for many body wave function is a subject I'm going to talk about. So continuous measurement consists of 2 processes, the jump process, described by this jump operator, and the no jump process, described by this non-Hermitian Hamiltonian, as we discussed so far. And for each realization of quantum trajectory, that is specified by a sequence of measurement outcome. So at which time quantum jumps occurs and which type of quantum jumps occurs. And if a jump operator doesn't commute with the Hamiltonian, so this is usually the case. The measurement, every time a quantum jump occurs, then some actions will be performed on the system, and this action doesn't commute with the Hamiltonian. Then the outcome is that energy is not conserved. But interestingly, this action can heat up or even cool the systems. the latter interesting possibility has been discussed by Peter Zoller and his colleagues. But usually, it summarizes. So we consider hardcore bosons with nearest neighbor and the next nearest neighbor interactions. And the number of sites is 18, and the number of particles is 6. So this panel shows the lattice site versus time. And initially, the density is flat. But sometimes an atom is identified to be here, for example. Then the wave function collapse occurs, and the density is red, very high here. Then subsequently, it relaxes, and then at this moment, almost the density is uniform, and the second atom is suddenly measured at this location. Then we know that, oh, atom is there, so density is then quickly rises, and the third, fourth, and fifth, something like this. So let me show the results. So first atom is now observed here, and this is a subsequent relaxation. So density is almost uniform, and then second atom is detected here, and there is a big perturbation. But because atoms interact with each other, the subsequently atoms density becomes uniform, and third atom is here, the wave function collapses and then decays subsequently. So every time an atom is detected, high density region emerges due to the wave function collapse, which subsequently relaxes towards the equilibrium value. So now we know that at this even single trajectory level, there is a relaxation, of course, because of interactions. Okay, so then how about the kinetic energy? So I said experiment does know that there is a heating, and in this case, jump operator doesn't commute with the Hamiltonian, so there are either heating or cooling. In this case, it's heating. So every time quantum jump occurs, the kinetic energy jumps stepwise due to this heating effect. And the k equals 0 component decreases stepwise. And this is a quantum depletion. And this blue curve shows the real actual dynamics, and the yellow dashed line shows a Gibbs distribution. And actually, red dashed curve shows a new statistical ensemble we propose here, which we call matrix vector product ensemble. And this matrix vector product ensemble always agree with the real simulation. So there are two messages. One is a new statistical ensemble emerges. Here, Vm is a matrix of a jump operator. So this is unique to quantum measurement operators, and which describes quite well for this single atom, single many-body trajectories. The second message is this. Initially, Gibbs distribution deviates from the actual ones, but just a few quantum jumps, it converges toward a Gibbs distribution, even though we are discussing a single quantum trajectory. And this is, I think, is a very interesting suggestion. Actually, quantum jumps, I mentioned that heating occurs because jump operator doesn't commute with the Hamiltonian. But this actually mixes the state toward thermal equilibrium. And indeed, this panel compares the actual distribution versus the Gibbs distribution. Initially, we start from a uniform distribution, which is far from Gibbs. Okay, so it's the energy eigenstate, so deviates greatly from the Gibbs distribution. But just after a few quantum jumps, they almost agree. Notice that the effective temperature increases because every quantum jump heats up the systems. But as a consequence of this quantum jump, the distribution moves toward equilibrium state. So this is a unique quantum thermodynamics in open quantum systems, because temperature changes in real time. And the quantum jumps relaxes the system toward the Gibbs distribution. Okay, so this, by the way, some people might be interested in what happens for the integrable systems. And this is a panel shows for the integrable systems. I just eliminate next nearest neighbor hopping to make this integrable. Then we see that the relaxation becomes very slow. And agreement fluctuation is very large and doesn't seem to converge very smoothly. So at each quantum jump, relaxation is slow compared to the integrable systems. But interestingly, in this case, just after the few quantum jumps, is enough to smear out initial memory at a single energy levels. So technically, we can say the biased weight on non-thermal eigenstates, which are admitted by weak ETH for integrable system, is eliminated by just a few quantum jumps, because jump operator mixes those states and eliminates those exceptional eigenstates. So here we find that the jump operator acts as an integrability-breaking perturbation and helps the system stabilizes. So I think this might add yet another mechanism of why thermodynamics emerges so universally, and even at the quantum levels, because we observe. And observation itself helps thermalize by eliminating exceptional states. So finally, let me just spend a few minutes to introduce our recent results about testing thermodynamics using a superconducting qubit. The theory part of this work is done by Murashita and Funo, and experimental part is primarily done by Masuyama in Yasunobu Nakamura's group. So it is now fairly well established that measurement and feedback, one can outperform the conventional upper bound on the extractable work by the amount of information obtained by the Maxwell's demo. However, a few new situation arises when we perform a very high precision projective measurement. Suppose that this is a distribution of an observable, something like this. So it's broadly distributed initially. And we perform a very precise measurement because we want to control the system very precisely. The most precise measurement is a projective measurement, which just pick up a special values and project out all other cases. Then the state after the projective measurement, we have regions with vanishing probability distribution. So you know Jarzynski equality, how to derive that. So under such situations, Jarzynski equality has to be modified, because Jarzynski equality and fluctuation theorems concerns thermodynamic time reversal symmetries. For every forward path, there is a backward path. There is a one-to-one correspondence between forward path and backward path. And if you take the ratios, then the thermodynamic entropy production governs the ratio. So this is the idea behind Jarzynski equalities. There is one-to-one time reversal correspondence. But here, since we exclude some regions, so there must be some forward path which doesn't have the counterparts in the backward path. Okay. To see this, let me just remind you of how Jarzynski equality is derived using the Crookes fluctuation theorems. So this is the entropy production, and the expectation value of this is given by this quantity weighted by this probability distribution of forward distribution. forward path gamma, and probability distribution is P of gamma, is related to its time reversal counterpart by this Crookes fluctuation theorems. Then this part can be replaced by this just the sum over the backward probability distribution, which is usually sum up to 1. Because there is, as I mentioned, we assume that there is a one-to-one correspondence for all forward paths, then we have all backward paths. Okay. When measurement of the feedback is performed, the only modification is that entropy production is modified by the amount of information we get, because if we get information, the entropy is reduced. So there is some correction, and we get this new more generalized Jarzynski qualities. But now with projective measurement, some parts are eliminated. Those parts have no counterpart in this backward processes. So we have to move out that part, which we denote gamma. So eliminated part is a gamma. And for this process, there is no counterpart in the corresponding backward process. So the time reversibility is essentially lost for this special case. That's why we call this fraction the degree of absolute irreversibility. Usual thermodynamic irreversibility is only thermodynamically irreversible, but stochastically reversible. Here, this part fraction is not just thermodynamically irreversible, but absolutely irreversible. Now, so this is how Yasunobu Nakamura's group tested using superconducting qubit. And so this is the quantity, and the implication of this is that the amount of extractable work must be reduced by this amount. So this is negative. So there is some interesting trade-off relation which I'd like to propose here. So if we want to gain information to achieve better work performance, you need to make a precise measurement. However, the most precise measurement, that is a projective measurement, produces absolute irreversibility, which in turn reduces the amount of extractive work. So I think there is some interesting trade-off relation between the amount of information you get and the amount of absolute irreversibility. What is the optimal point? What is the absolute upper bound over this right-hand side? Is something I think we need to investigate in near future. Okay. So Nakamura's group tested this using superconducting transmon qubit with this 2-point energy measurement. And usually, what I learned from this collaboration is that usually testing Jarzynski equality is hard because we have to probe many negative entropy producing terms, which is very rare. But superconducting qubit, they perform millions of experiments in quite a short time. So they can very effectively probe such very rare event. And moreover, they have this qubit, so they have. Let me just spend 2 minutes. So sorry. That's my time. So I still have some time. Good. So the nice thing of this is that they have two-level systems, and they can intentionally prepare the fraction of excited states by just applying a microwave. So their initial temperature is tuned, and they can test even negative temperatures. So aren't you interested in whether the Jarzynski equality applies for negative temperatures? And they could do that, okay? And they have done that. So initially, they prepare some initial states, the canonical distribution, and then perform the measurement. Depending on if the measurement result is the ground state, they do nothing. Okay. But if the measurement result turn out to be excited states, then they apply a microwave pulse to extract this energy, and their final state is ground state. So they get some work. So in the forward process, there are only two paths. In the backward process, they start again from the canonical distribution, but now there are 4 different possibilities. That is, initial state is excited state, final state is excited state, ground state, excited state, ground state, and ground state, excited state. There are 4 possibilities. Of them, the dashed curve processes are absent in the forward process. So those 2 events give the absolute irreversibility. Very nice, excellent case. And this is the results of their measurement. So the vertical axis shows those quantities, and the horizontal axis shows the inverse temperatures. Notice that this is the negative temperature regime, and this is the positive temperature regimes. And the dots shows the measurement results of this quantity, and the solid curve shows 1 minus gamma. They agree excellently. So they have confirmed that this relation holds for any effective temperature, even at negative temperatures. Very nice. Now, as a second experiment, they measured how much work can be extracted from these systems. And this panel shows eta is the work divided by the amount of information they extract. So this eta gives the information to work conversion efficiency versus the feedback error. So remember that in the experiment, they perform a second energy measurement to check whether their final state is indeed the ground state. Sometimes it turns out to be excited state. Then this is simply the feedback error. And they show that the dots shows the measurement results, and they, even at 0 feedback error, there is the conversion efficiency is below 1. And this quantity is precisely given by this quantity. So because the measurement is actually the QND and sharp, there is a non-zero absolute irreversibility, which sets the upper bound here on the efficiency. This result is indeed checked by their experiment. Okay. So to summarize, we have discussed non-equilibrium many-body dynamics under continuous monitoring by focusing on quantum statistics, critical phenomena, and full quantum dynamics, and single trajectory thermalization. And in the second part, I have discussed non-equilibrium equalities with absolute irreversibility. Superconducting qubit turned out to be an excellent platform to test this phenomena. And by the way, this absolute irreversibility turned out also to be a key to resolving Gibbs paradox. Okay. Thank you very much for the kind attention.
Thank you very much. Are there questions? Let's start at the front.
Thank you, Masahito, for the very nice talk. Yes. I have actually 2 questions. The first one is, do you take it into account, or how do you integrate the imperfect detection